Okay, take a look at number 7. This is a review question, and it leads in perfectly to what we're doing today. All right, you have a box of 11 calculators. 3 are defective, 8 are good. You're going to pick 2 calculators, with replacement. What's the probability that both are defective? All right, here we go. Probability, defective. First pick. What's the probability you get a defective calculator out? How many defective calculators are there? 3 out of 11. What do I do with that defective calculator? Replace it. So now for a second draw, what's the probability I get a second defective calculator? 3 out of 11. And how many times did I just choose? What do you want me to do? Add or multiply then? There you go. So this ends up being 9 out of 11 times 11. 121. All right, no big deal. Nice little review problem. Do you remember what I call those 2 events? I call them 2. Did the second probability rely on the first one? No. So these 2 events are called independent events. That's what we're going to look more at today. All right, except you won't see the words with replacement and without replacement. So I don't know if they're independent of each other or they do depend on each other. But everyone, all right, why these 2 are independent? Because did it matter what I did first? Did not matter. All right, did not matter what happened. The second probability did not change. All right, so let's go back in your packet now. Let's look more at the independent events. All right, little brake pads here, transmission fluid. Go ahead and read through it. We're bringing your car into the shop. Probability you're going to need transmission fluid, 0.38. Probability you're going to need brake pads, 0.28. And the probability you're going to need both, 0.16. Are these 2 events independent of each other? Now, you don't see replacement without replacement, so as right now, we have no idea. All right, no idea if these 2 events needing transmission fluid or brake pads are independent. So here's how we're going to test today. 2 ways we're going to test. First way is exactly how we did this one. All right, how we just did the 2 defective calculators. And that is straight definition, probability of transmission fluid and brake pads. If they're independent of each other, this probability should be the same as the probability you need transmission fluid times the probability you need the brake pads. If they are truly independent of each other, this probability should equal to these 2 multiplied. Hey, isn't that what we just did? All right, that's what we just did. If 2 events are independent, it's equal to the 2 separate events multiplied together. So let's test it out. Oh, sorry. Let's test this out, see if they're equal to each other. Oh, I love doing this. Here we go. Oh, this would be good. 21. Anybody for 21? Jess, you're 21? Yeah. Okay, ready to go? And it's right in the problem, so I'm not asking for any magic here. Probability you need transmission fluid and brake pads. What did I tell you? 0.16. So is 0.16 equal to, here we go, Jess, stay with you, probability you need transmission fluid from the problem? Oh, not yes or no. I'm just asking, what's the probability from the problem you need transmission fluid? 0.38 times, what's the probability you need brake pads? 0.28. Let's find out, are these 2 equal to each other? Yep, go ahead. What do you end up with when you multiply on the right side? 0.16. Obviously not equal to each other. So are these two independent of each other? No. If they were independent, they'd come out to be equal to each other. All right, so we're going to say these two events not independent, but dependent on each other. Because they didn't come out, the probabilities didn't come out to be the same. If they came out to be the same, they would be independent of each other. That's not the way I want to look at it, though, today. I want to look at a second way to show that they're independent. Ready? Probability you need transmission fluid given you already got brake pads. Listen, I'm going to do my best here to make this clear. It shouldn't matter if you got brake pads or not. If these two events are independent, this probability should still be equal to the probability you got transmission fluid. It shouldn't matter what happened, right? Everyone agree? It wouldn't change this probability. If these two events are independent of each other, brake pads and transmission fluid, it shouldn't matter. The transmission fluid, the probability should stay probability that you got transmission fluid, regardless if you got brake pads or not. That probability should not change. Did it change here? Because I put it back, right? Didn't change the probability. That's what I'm going to try to stress to you guys is that probability of T should not change regardless of what I do. Let's find out. Here we go. Who's got 2? Need some help from 2. Not here. Mark, 1 job. 9. 9? Okay, here you go, Gianna. Ready? Probability you get transmission fluid. 0.38. 0.38. Oh, you're right. Sorry, 0.38. Thank you. Didn't we do this yesterday? We did this yesterday, didn't we? All right, no problem. What goes on top? The probability you got both, right? The probability you got both. So go ahead, Gianna. What's the probability I got both? 0.16 over, remember the denominator? Given I got brake pads. So 0.16 over, what's my brake pads? 0.28. Let's find out, are those the same? .16 divided by 0.28, about what? 0.57? Yep. Obviously not equal to 0.38. So that changed the probability. Hey, listen, please, listen. The fact that I got brake pads, didn't that just change the probability I got transmission fluid? Which means what? Can they be independent then? No, one depends on the other. Okay? Because if they were independent, these two should have been the same. It wouldn't have mattered if I got brake pads or not. But it did change the probability I got transmission fluid. So that means they depend on each other. Hannah, you all right? Okay, so conclusion here. Here's the conclusion for today. Independent if must be important because he's doing it all in caps, huh? Or he's angry. Isn't that how you guys text? If A and B are going to be independent, the probability of A given B should be what? The probability of just A, yeah. Doesn't matter if I threw B in there or not. Okay? If they're independent, the probability of A should remain the same regardless of what I throw in there at you. Or look for Anybody remember the term? I just used it on the defective calculators. What was the term that said, oh, it's independent? What did we do to the defective calculator once we picked it? So look for with replacement, yes. Don't forget of where you came from. Okay, we knew they were independent in the past because I saw with replacement. I replaced it. Okay? All right. My show is basically over. I'm really going to turn it over to you guys now. Okay, hopefully you like the people you're working with or around. I am going to help you out with the independent-dependent stuff, but I want to see you guys, as far as review purposes go, find these conditional probabilities I'm going to give you. I gave you a two-way table with the probabilities already in there. We're comparing hair color and eye color now. Hair color and eye color. So what I need you and your group to do first is the following. Find the probability you're going to have brown eyes given you already have blonde hair. That's review from yesterday. Nothing to do with independence or dependence. So within your group right now, talk it over. Using your table, what's the probability you're going to have brown eyes given you already have blonde hair? All right, you already have blonde hair. So out of all the people who have blonde hair, what's the probability you're going to have brown eyes? So go ahead, go to work. I'll get back to you in a minute. Okay, let's go back to you guys. Here we go. 15. Well, what's the probability you're going to have blonde hair first? Blonde hair. Regardless of eye color, blonde hair. 0.35. So your denominator should be 0.35 because I'm only looking at the people who have blonde hair. Out of all those people that have blonde hair, what's the probability you have brown eyes? 0.10, yep. And I don't like decimals in the fraction, so let's clean that up a little bit. You can give me as a percent, remember, or you can leave it in a fraction form, 2 out of 7. Everyone all right? Okay, take another minute right now. Let's do another one. Find me the probability you have red hair given you have green eyes. Finally, some representation, huh? Yeah. In a word problem, my man. There you go, stealing souls. Here we go. Red hair given green eyes. Everyone gets thrown in every once in a while. Okay? So what's the probability you're going to have red hair given you already have green eyes? All right, here we go. 20. Ready? Okay, first of all, green eyes. That's all I'm looking for. You're already given green eyes. What's the probability of green eyes? No, regardless of your hair color. 0.25. So there's my denominator. Out of everyone who has green eyes, what's the probability of red hair? 0.15. Perfect. And then that reduces down to 3 out of 5. So you got a 3 out of 5 chance if you have green eyes, you'll have red hair. All right, now let's take over for what we're doing today. Do you think, not really what you think, we're going to prove it mathematically, having red hair depends on having green eyes? Or are they totally independent of each other? It's not what you think. This isn't a personal opinion. I want to prove this mathematically. So here's what I'm asking for. Having red hair depend on, I don't know, what should I put? Green eyes, GE? Is that all right, everyone? Green eyes. If they are truly independent of each other, this probability should be equal to the probability of what? Red hair. Everyone's seeing that. Doesn't matter if you have green eyes or not. So let's find out if they're actually independent or dependent of each other. I believe we already found out the first one, right? We found this to be 3 out of 5. We just did that in part B. What's the probability of red hair? Let's go back. Red hair, 0.20. We want to convert that back into a fraction. Probability as a fraction that you have red hair, 1 out of, up. So what can we say here? What did we just find out? They depend on each other. Yes. All right. Having red hair depends on having green eyes. Yes. So they're not totally separate from each other. There is some dependence. Do we see how this is starting to work a little bit now? Okay? That probability should not change regardless of what occurred. Okay, they should still be equal to each other. All right, let's try a couple more out. This is what's good about today. It should go pretty quick now. All right, we surveyed the old 6th grade. Results of their favorite subject depending on their gender. We did put a table in for you. So absorb that table here. Does it appear that the preference for math as a favorite subject depends on the gender? All right. So does math being your favorite subject dependent on the student's gender? All right, so we got to test both male and female. All right, so let's go female first. So what do we have to test? The probability that you prefer math, given you're already female. And if they're independent, go ahead. Good question. Got me there. What's it? Calm down. 18 plus 10 plus. No, it should be 10. Yes, it should be. Because this adds up to 56 down. Yeah, I know. One job. Thank you. All right. So the probability you prefer math, given you're female, if they are independent, should be the same probability that you prefer math. All right, let's find out. You and your group right now, go ahead, find both probabilities and we'll talk. All right, let's hear back from some people now. Here we go, 7. I have a 7 in the house. 7, here we go, man. Probability you prefer math given you're already female. What are you already given? You're given that it's already female. So how many females do I have? 30. And how many of those 30 females prefer math? 8. Okay? Now, what's the probability you prefer math? Regardless of your gender here, you prefer math. 57, all right? Now, I look at those fractions and I'm like, maybe they're equal. We'll see. What can you easily do now to see if they're equal to each other? And yeah, go in your calculator, do the decimal equivalent. 8 out of 30 comes out to be about 0.27. And 18 out of 57 is about 0.32. So, yep, they depend on each other for female in math anyway. What about male now? Is the probability you prefer math, given that you're male, equal to the probability that you like math or prefer math? Well, we already know that's 18 out of 57. What about this probability now? That you prefer math given you're male. Here we go. Who's got 2? Not here. I have surgery. 9. Who has 9? How many males are there? There are 27 males, and how many prefer math? 10? Ooh, I have no idea. I got to do the decimal equivalent. So 10 out of 27, 0.37. And we already said that was 0.32. So is gender independent of what if you prefer math or not? No, it depends, doesn't it? It depends on your gender if you like math or not. That's what we just proved. All right, depends, okay? So yes, there is dependence on gender. All right. You guys have about 3 minutes right now. Let's do social studies now. Does it depend on your gender if you like social studies or not? Go right ahead. You and your group right now. Does it depend if you are male or female if you like social studies? Well, you want to, if they are independent of each other, the probability you prefer social studies given you're female should be the same as preferring social studies out of. Okay. And remember, there's 30 females though. You're doing the reverse. You're already given your female, so that means out of 30, there's 10 out of 30, right? Some of you guys find it out a little different, huh, than math?
Why do you want to pull two defective calculators? I'm serious. Not about logic. Why do you want to pull two broken calculators? You knew going in three were broken. If you knew three were broken. If you're running to like the tens, like no. Look at it.
Okay, here we go. So I give you guys some time to work on the assignment. So let's see. We knew math depends on the gender. If you like math or not, it depends on your gender. What about social studies? Well, here we go. Probability. You prefer social studies given you're female. Well, there's already 30 females, and out of the 30 females, 10 like social studies. How many like social studies? Well, out of the total of 57 total students, how many like social studies? 19, right? And you found out what? 0.33, 0.33. Okay, no problem. So far, they're independent. Let's check on the males now. Probability you are male and you like social studies. So there should be 27 males. How many like social studies out of those 27? 9, and we already figured out, 19 out of 57 students enjoy social studies the most, and that ends up being, again, 0.33, and so does it matter your gender? They have no relation. No, it does not matter. All right? There is no dependence. They are independent of each other. Gender does not affect if you like social studies or not. Last one. We're going to run into a little curveball here. Not a curveball, but a little problem. I don't know if some of you have started this already, but we run into a problem. Okay. Not even a word problem here. Just here's the probability of A. Here's the probability of B. What was that from yesterday? Both. That's or, right? That's the or, not the intersection. A or B. That's the union, remember. Is 0.8. Are A and B independent? All right, well, let's figure it out, right? Probability of A given B, if they're independent, should be equal to the what? The probability of A. Okay. Everyone, let's fill in the right side. What's the probability of A happening? 0.6. Let's figure out the probability of A given B. We run into a problem because on the bottom we put the probability of B, which we know is 0.5. But dig deep here. For yesterday, what did we usually put in the numerator? Both. And they gave me the or. I can't use that. I need, on top here, the probability of A and B happening. All right, so I cannot put that 0.8 in there. But there's a way I can find it given this information. All right, I'll give you a little formula if you'd like to remember it or not. If you ever want to find the probability of A and B happening, it's the same thing as the probability of A plus the probability of B. Anybody know what I do with that A or B? Minus the probability of A or B. Who's got 17? Hey, Shannon, how are you? I'm doing well too, thank you. Probability of A plus the probability of B minus the probability that A or B happens, 0.8. So what's the probability of both of them happening at the same time? Point. Yep. And that is what I will plug in up top. 0.3 divided by point. Yes, Austin.
Could you just cross multiply? Like 0.5 times 0.6, and you get 0.3.
Well, here's the problem, though. I don't know if they're independent. If they were actually equal to each other, yes, you are correct. But if they're dependent, then you'd always get that they're independent then, right? Okay, I like it. What are you guys figuring out here? 0.3 divided by 0.5 came out to be 0.6. So what do you notice? Are A and B, they are independent of each other. Get going. Get going.